Okay, now we're looking at section 6.2, which is using proportions to solve geometry problems. We need to start off this one with some properties we have about proportions. If you've already seen section 1, we look at the cross product property. And that tells us we can take the cross product and a proportion and allows us to solve. It may be good to look back at 6.1 to see that cross product and see how you'd solve, because really these properties, we don't use them so much to solve. They're just things we need to be aware of. Ways the problems may need to be manipulated at times, and just ones to look for as we start dealing more and more in proportions and leading to similarity. The first one we have is the reciprocal property, and that tells us if two ratios are equal, then their reciprocals are also equal. So if I took AB and CD, each my two ratios that are equal to each other, and I flipped them, which is really what that means when I'm talking about the reciprocal, I would have B over A equals D over C. Now, this property tells us that's true. Let's use that cross product idea just to make sure it turns out the same, because cross product, we said, well, we can go and multiply the diagonals. I would have A times D equals B times C in this proportion, and this one would be A times D equals B times C. So it would be the same. So even though I flipped them and took reciprocals of both, make sure it's both of them, it still turns out to be the same proportion. If I was solving for a value, maybe C in this whole thing, I could still find that same value. Our second property says if you interchange the means of a proportion, then you form another true proportion. Our means are going to be B and C. So if I switched these two, now C is down underneath A, B is above, they're also same. Again, let's look at cross product. A times D equals B times C, and A times D equals B times C. The cross product stays the same, therefore if we were solving, it still maintains. So we may see the means flipped at times. Doesn't change it, we just have to learn how to identify that. Last, in a proportion, if you add the value of each ratio's denominator to its numerator, then you form another true proportion. So now I'm going to take this B and I'm going to add it up to A. I'm going to take D and add it up to C. Now, I'm not adding the same thing to both sides, I'm adding the denominator. So it becomes A plus B over B and C plus D over B. If we look at it really, I'm taking A over B and adding B over B to it. And that gives me A plus B over B. Well, really all that is 1. So in fact, I'm adding 1 to both sides here. Same thing applies to C over D. When I add D over D, I'm adding 1 to both sides. And anytime I have an equation, I can add the same value to both sides. This time it just has to be 1, and it's just disguised a little bit different. So another one we may have to be aware of. So let's look at some proportions. We're going to see how these show up and start to fill in some missing values. We're not going to deal with solving the proportions so much. It's for now taking these properties and rewriting them. So I have x over 9 and y over 20. I want to get to x over y equals what? So if x over 9 equals y over 20, well, I went from x over 9 to now I have a y underneath. So really that y looked like it went from the top right to the bottom left. If I look back at my list, I think which one of these would the y, or maybe the c value in this case, move? Well, in our second one, that c moved down, and that's interchanging the means. So in this one, let's move that 9 back up, and we get x over y equals 9 over 20. Now, let's quickly double check to make sure that works. If I did the cross product of this one, I would get 20x equals 9y. Cross product of this one, I would get 20x equals 9y. They would be the same. Not too worried about what x and y are respectively. I just know I would get the same value. It's set up the same way. We just changed the way we looked at it. Next one. 14 over 3 equals x over y. Then 17 over 3 equals what? Okay, well I have the 3's. Those are the same. This isn't an x or a y. This is kind of new. But if we think for a second, where would we get 17? We're not going to introduce something new, but if I took that 3 and added it to 14, I'd get 17. So this is actually our third property we just looked at, which says we add the denominator to its numerator and we get another true proportion. So I add the denominator y to x, and I would get x plus y over y. Next one, 8 over x equals 3 over y. Well, this one probably looks familiar. This one, I'm again switching the 3 and the x, so it would be x over y. Last one, x over 6 equals y over 15. New one says x plus 6 over 6. Well, looks like I added 6 here. So I'm going to add 15 on the other side and get y plus 15 over 15. Let's take a minute and look to make sure this is still the same proportion. So I have x plus 6 over 6 equals y plus 15 over 15. Should be an issue one, so I'm going off the notes here. Let's just make sure it does work. So I get 15x, or 15 times the quantity x plus 6. Got to be careful with that distributive property. 6 times y plus 15. If I distribute, I get 15x plus, well, I need 15 times 6. Well, let's find out what that is. Looks like I get 5 and 6 is 30, so it turns out to be 90. So 15x plus 90 equals 6y, oh, 6 times 15, that's still 90. And if I go ahead and kind of subtract 90 from both sides, I would get 15x equals 6y. From here I could also divide both sides by 3, and it comes down to 5x equals 2y. Well, let's look. Let's check this one now and see if it's the same case, our original one. So if we can reduce it down to be the same thing, we know the proportions are the same. So x over 6 equals y over 15. Cross product gets us 15x equals 6y. I can divide both of them by 3, and I get 5x equals 2y. They match. The proportions are set up the same. We won't use the proportion or these rules too much in solving, but it's just key thing knowing. As we go forward with proportions, however we set them up, we switch the means, we take the reciprocals, or we add the denominator to both of them. As long as those cross products work out the same way, we'll be all right. So let's take these proportions and now start looking at applying it to geometry. So they give me a proportion, C over B, or CB over BA, equals DE over EF. And I need to find BA, which is right here, this length out here. So if I take CB over BA, DE over EF, they gave me values I can already work with. CB is 6, DE is 4, EF is 7, and I'm looking for BA. Well, just by setting it up, plugging things in, I've made it into a basic proportion we can do cross product with. So I would get 6 times 7 equals 4 times BA. Gives me 42 equals 4 times BA. Divide everything by 4. And 42 would actually become 21 over 2 for BA. Or if you want to make it a decimal, it's a nice decimal because we're dividing by 2, just 10.5. Either one would work. On a test, you'd probably see it as the fraction, but it's good to see if we can find it at that 10.5. So BA, let's put it there, 10.5. Okay, let's look at a different one. Same idea here. Now we're just going to set up a little bit different, because you notice these were kind of set up stacked already on opposite sides. Let's look at a new one here. So now I have XW is 12, WV is 5, YW is 24. They give us a proportion, so let's set up what we have. XW, XV, YW, ZV. And it looks like we're trying to find ZV, which is right here. So I know XW is 12, XV. Well, XV is from this top vertex to this bottom vertex. So it's not necessarily just a 5, it's the whole thing. Or 12 plus 5. Then we have YW, that's 24, and ZV, again, what we're solving for. Well, before we do cross product, let's clean this up and make this into a 17. So 12 over 17 equals 24 over ZV. We're now going to do cross product. So I'm going to have 12 times ZV equals 24 times 17. Looks like I'm going to need a calculator. So 24 times 17 gives us 408. 12 times ZV equals 408. 408 divided by 12, so I'm just going to divide both sides by 12. Gives me ZV is 34. Okay, so you'll see some more of these on the homework. For right now, they'll give you the proportion, plug them in, solve the proportion correctly. Just make sure you're picking the right values. A good example of that is knowing that XV is 17 and not just 5 or 12, but finding the correct values and simplifying. Later, and then in these future sections, you're actually going to be given the diagram and you're going to need to create the proportions. And we'll get to that when the sections come. Okay, last we have a couple terms to look at, and first is a scale drawing, and that's going to be a drawing that is the same shape as the object it represents. Now, examples of a scale drawing: a map, a blueprint. Those would be something that's going to be the same shape. It's a smaller form of what the object is. If we look at a blueprint of a building, we're not going to take the whole building and carry that design around with us. We want a smaller form that actually works. So the blueprint would work for us. Now, how we say how small it is to how big it is to the actual object is the scale. And that's going to be a ratio. And if we remember ratio, that just means it's a fraction. And that's a ratio that describes how the dimensions in the drawing are related to the actual dimensions in the object. So now this is that ratio that tells us. How are we going to compare? Is it a 1 to 2, 1 to 5, 1 to 12? Maybe it's a 1 to 54. 1 inch on the scale drawing represents 54 feet of the actual object. Well, that sounds like a good scale to work with. Let's look at an example of a model train. So you purchase a scale model of a model train. The model states the scale is 1 inch to 54 feet. So that means if we look at the model we have here, that 1 inch on that model is 54 feet of the actual object. Because we're not going to buy an actual train. We want the small representation of it. So 1 inch on that train is 54 feet of the model. So maybe we say, you know what, something is 2 inches on the model. Well, we multiply it by 2, that'd be 108 feet of the actual object. 54 feet to 1 inch, so that's what we're comparing. Now, we say that's a ratio, so I'm actually going to write this ratio instead as a fraction, which is 1 inch to 54 feet. So, now they tell us if the model is 10 inches long, how long is the actual train? So I'm going to use my ratio, 1 inch to 54 feet, and make it into a proportion. So this is my ratio, and the problem wants us to say, okay, now it's looking at length. So it's 10 inches long. So the model is 10 inches I want to find the actual. So 1 inch to 54 feet equals 10 inches to what? Well, we can just do cross product. And before we do that, it's always good if you write that ratio and the units are different. You can use that to help you see that. 1 inch to 54 feet, well, inches need to make sure they go with the model. Now, it won't always be the case, but it's nice just to double check as we set up, because I definitely don't want to put 10 inches down here, because that would give me 10 inches on the actual object represents what in the model. And that'd be a very small value dealing with the ratio we have. So I do cross product. I get 1 times x equals 54 times 10, and that gives me x is 540 feet. So length of the actual train is 540 feet. Okay, now we look at the actual height of the train is 27 feet. How tall is the model? We're going to use our same proportion, or same ratio, 1 inch to 54 feet. This time, we're looking at height. So we know it's 27 feet actual, and we want to know how tall is it in inches. We do cross product. We get 54x equals 1 times 27. 54x equals 27. If I divide both sides by 54, I get 27 over 54, or x is 1/2. Well, what that means is the model height is 1/2 inch. We know it's 10 inches long by 1/2 inch tall. 1/2 inch by 10 inches, and the real thing